The last were only rotational changes. The order of energies like electronic and vibronic are most energy associated next to vibrational or vibrational rotational, and least energy associated are rotational spectra. Now, when that energy transition takes place, you get vibrational spectra. To explain vibrational spectra, different models are proposed. Okay, so first is harmonic oscillator model. Now, in harmonic oscillator model, it is considered that the molecule is performing simple harmonic motion like an oscillator. The infrared radiation, that is the electromagnetic radiation from 10,000 to 100 centimeter inverse, is absorbed by a molecule, converted by an organic molecule into energy of molecular vibration. Molecule is going to absorb this energy and its vibrational state will change. That is, from say this level, it will jump to this level, or from this level, it will jump to this level. So, vibrational level is going to change when a molecule absorbs infrared radiation. Now, this absorption is quantized. To explain this, quantized means the energy difference between the one level of vibration and other level of vibration is fixed. This energy is fixed. When the electromagnetic radiation energy associated with that electromagnetic radiation matches with the energy difference, that quanta of the energy, that packet of the energy, that discrete quantity of energy is absorbed by the molecule, and then its vibrational energy increases. If it happens that suppose molecule is at this level, energy is falling on the molecule, it may absorb it. See, there is a chances that it may or may not absorb it. See, if the energy of the electromagnetic radiation is not matching with the any of the transition where molecule can increase its vibration. So from here it cannot jump to here, from here it cannot jump to here. Suppose the energy is equivalent to suppose from 0 to 1, and it is between 1 and 2. Okay, it is somewhere suppose here. So it will not absorb that energy. Okay. So in this harmonic oscillator model, the molecule is considered as say a diatomic molecule. Is suppose there are two masses m1 and m2 represented by each atom, and the bond is represented by a spring. Then, as the law which is applicable for this ball and spring model of oscillator, it is Hooke's law. So force involved in this oscillation is equal to minus F multiplied by delta R. R is distance between two atoms. It is bond length. So delta R will be change in the bond length. F is force constant. It is more specifically restoring force constant. The original spring, when it's compressed or when it is stretched, in both cases it tries to regain its original position. So force is there within the spring. That force is called as restoring force. Now, the negative sign indicates that it is active in the opposite direction of the change in the distance between two atoms. Like if two atoms are getting stretched, the force will be applicable, force is being applied in the opposite direction, that is towards compression. Okay, I will read out the description below the diagram. A simple harmonic oscillator like this is a mechanical system consisting of a point mass connected to a massless spring. So these are the point masses, and the spring is considered to be massless. The mass under action of a restoring force proportional to the displacement of particle from its equilibrium position and the force constant F, also known as K, of the spring. Now, if we try to draw a diagram of energy of the system versus the distance between two point masses for perfect harmonic motion, you will get a graph of this dotted line. I hope you can see that. Let me magnify it if possible. Okay. At certain distance, the see, if you see the middle point over here, I hope the pointer is visible to you. Okay. The energy is minimum. That means the value of R is the best value of R. That is the can say the bond length where the energy is minimum. If you go on either side, if you go on increasing or you can go on decreasing, ideally the energy goes on increasing in the parabolic order. Okay, so it is a parabola. The energy will increase like this. This is related to the point masses connected via spring. Okay, it is in that case. But in case of molecule, that ideal vibrational motion, ideal harmonic oscillation motion is not observed. In case of molecules, that is, now we are moving into the next part, vibrational spectra, second point, unharmonic oscillator model. Now, this type of spectra, I should not call it a spectra, this type of graph, you have seen it before. Not in IR, somewhere else. Do you recognize that graph where you have seen it? We have seen such graph in case of hydrogen bond formation, H2, formation of sigma bond. Okay. The actual potential energy of the vibrations fits parabolic functions fairly well, but near the equilibrium internuclear distance. That is, at the lower level only, the harmonic graph matches with unharmonic graph oscillator model of the molecule. As you go at higher and higher energy level, the distance between energy levels goes on decreasing. The more potential function more closely resembles the potential energy of vibrations in a molecule for all internuclear distances unharmonic oscillator model. So we are going to compare the model of molecules in this region only. That is for say first fundamental mode of vibration, then first and second modes of vibrations. In that region only, the unharmonic oscillator model overlaps with harmonic oscillator model. It is like we are focusing on this part of the curve, the lower part of the curve. On x-axis, you have the change in the distance between atoms. On y-axis, you have potential energy which changes as a function of r, that is distance. Okay. Now try to correlate this with over here. Okay. So this is, if I want to make it more specific, what I can draw is can draw something like this. Okay, so these are the modes of vibration. Potential energy increases on y-axis. The distance between atoms changes on the x-axis. I hope you could correlate that. So change in the energy of vibration. So change in the energy of vibration is equal to the energy associated with n1 plus position minus energy of nth position. Now, if you want to compare this with this diagram, say n is equal to 0. N is equal to 0. So, when the compound, the molecule jumps from say n0 to n plus 1, the change in the vibrational energy will be energy of 0 plus 1 level, that is energy of this level, minus energy of nth, that is energy of 0 level, that is 0 level here. So we are talking about this energy difference. Now, how to correlate this energy difference, energy that is absorbed, and the change in the vibrational energy of the molecule to the energy of the electromagnetic radiation. So generally it is equal to, energy is equal to H nu. But here nu is that of frequency of the oscillation. Now what is being oscillated? Molecule is being oscillated. If you multiply that with Planck's Planck's constant, you will get energy of the electromagnetic radiation falling on the molecule. So this is how that quantized part comes. Okay, that's why the energy absorbed by the molecule is always quantized. Okay, I will read out the explanation besides the graph. The energy difference between the transition from n to n plus 1 corresponds to the energy of the absorbed light quantum. The difference between two adjacent energy levels get smaller with increase n until the dissociation of the molecule occurs. Dissociation means breakdown of the molecule occurs. Now it is related to something else also. See, if the energy difference between higher and higher molecular level, higher and higher vibrational level goes on decreasing, and it is coming near to one another, it may happen that suppose molecule is at this level. I will clear the ink so you will understand it better. Okay, suppose molecule is at this level and it is absorbing the energy which is similar to this transition also and this transition also. So molecule can jump from n to n3 or n4 also. Or more I say, suppose molecule is at this level. Molecule is at this level. Now this energy difference and say this energy difference is very much similar. So if electromagnetic radiation falls, which is approximately equal to this energy difference, the molecule may jump into higher vibrational level. It may be equal to any of this. It may be equal to this also. It may be equal to this vibrational state also. Say 4 and 5 or 5 or 6 and so on and so forth. Okay. So because of this, weaker transitions called overtones are sometimes observed. This corresponds to delta nu, that is change in the vibration level by 2 or 3. That means instead of jumping immediately in the next vibration level, molecules jumps to directly second or third vibrational level. It happens when the energy difference between second and third vibrational level is very small. In that case it occurs. Okay, this is third. I by mistake shown that both at second. Okay, so when that energy difference is small, overtones are observed. Okay, so I will read out it again. Weaker transitions called overtones are sometimes observed. These corresponds to delta nu is equal to 2 or 3, and their frequencies are less than 2 or 3 times the fundamental frequency delta nu because of unharmonicity. Unharmonicity means because they are closer to each other. Okay. Typical energy species for vibrational levels are on the order of 10 raised to minus 20 joules from Boltzmann distribution. It can be shown that at room temperature, typically 1% or less than that of molecules are in excited state. In the absence of external radiation, thus the absorption transitions observed at room temperature are from nu is equal to 0 to nu is equal to 1 level. In simple line, the last paragraph states that at normal room conditions, most of the molecules, okay, most of the molecules are at ground state of vibration. They are at n is equal to 0. They are over here. And only 1% of the molecules are at this stage. So when energy falls on the molecule, it is more probable that these molecules, that is n is equal to 0, will absorb the energy and jump to n is equal to 1, nu is equal to 1. Okay, so these are the most probable transition. Now, in vibrational spectra, now we are coming to the third part of it, rotation vibrations transition. That is, not only the vibrations are changing, it is associated with the rotational changes. The vibration spectra appears as a band rather than line. What does it mean? Now, if you remember the basis of spectra, a single line in the spectra, this is spectra. And if you observe single line, rest everything is blank. It means only single transition is taking place. And instead of line, if you observe a band, it means there are many transitions which are similar in energy, they are taking place simultaneously. The similar thing I can explain in case of electron. Suppose electron from one energy level is jumping to the another energy level by absorbing electromagnetic radiation. So in the spectra, it will be single line only. Okay, it will be a single line only. Now, this is in case of atom, but in molecules, instead of having only discrete energy levels, there are closely associated electronic levels. Okay, so molecule can jump from, say, like this, it can jump like this, or electron may jump to a higher energy like this. Now, these three transitions are very similar in energy. These three transitions are very similar in energy. So their bands will appear adjacent to each other very closely. Their lines will appear in the spectra very close to each other, giving rise to appearance of small band. Now this was regarding electrons. What about then vibration? In case of vibration, see, in case of vibration, suppose vibration can change from 0 to 1 level, vibration can change to 0 to 2 level, or it may change to 1 to 2. Okay, if that is the case, then you will observe three distinct lines. But in reality, sometimes it is observed that there are very compactly arranged lines as if they are bands. As if they are bands. Now, what does this suggest? That there are more levels associated with one primary level, like they are corresponding to these rotational energy levels. Large lines are related to vibration, small lines are related to rotation. Because of these rotational energy levels, instead of getting discrete lines, you are getting small bands. The vibration spectra appear as band rather than lines. When the vibrational spectra of gaseous diatomic molecules are observed under high resolution condition, each band can be found to contain large number of closely separated components, band spectra. Now, if you have understood my explanation, you will understand this second statement. When for a diatomic molecule, gaseous molecule, the spectra was observed, the vibrational spectra was observed, those bands were observed as lines which are compactly arranged. The structure observed is due to single vibration energy change is accompanied by a number of rotational energy changes. The form of such vibration rotation spectra can be predicted from energy levels of vibrating rotating molecules. So they give rise to vibrational rotational bonds. There is another way of looking at the vibrational models. Suppose this is a mass attached to fixed support via spring. Observe the central diagram only, don't observe the graph. This is the mean position 0. The mass can be stretched down at maximum distance traveled by it is y, and the displacement is, you can say the position is a and displacement is y. Okay, the distance traveled is y and it raises to a position. Similarly, when you will release the mass from that distance, y distance, it will travel because of the spring motion, restoring force within the spring, and it will reach to minus a position by traveling minus y distance. Okay, now if you have understood this, try to correlate with that graph. At mean position, the energy, potential energy of the system is 0. As the mass travels distance y, it reaches the maximum at position A. Again, because of the restoring force, it reaches to 0, and then again it reaches to minus A. This is a parabola. Okay, so this Hooke's law we have seen just now. F is equal to minus ky, where y is the distance traveled and k is the restoring force. So, using, you can say, extrapolating this, we can say vibrational frequency, the natural frequency of the oscillation is Vm is equal to 1 by 2 root k upon m, where Vm is the natural frequency of that vibrating body. In case of molecules, the two atoms connected via single sigma bond. M is the mass of the body attached. In case of molecule, it is mass of atom. K is the force constant of the spring. We can talk about force constant of the bond. So, the equation can be modified to describe the behavior of the system consisting of two masses also, M1 and M2, connected by a spring. Here, it is only necessary to substitute the reduced mass mu of the single mass m, where mu is equal to m1 m2 divided by m1 plus m2. Now, reduced mass refers to the combined mass of the two point masses, two atoms in that case. So the vibrational frequency of such system is given by What is being changed is only mu is been introduced. Okay, so mu is m1 m2 divided by m1 plus m2. So there is slight change in the equation over here. Okay, this mu is over here. Okay, so what happens is it should be multiplication sign here. Okay, now it is okay. So if you give that quantum treatment to the above equation, so change in the energy, that is when one vibrational level is converted to another vibrational level by absorbing the electromagnetic radiation, so that change is equal to H into Vm, fundamental mode of vibration. So it will be equal to H divided by 2 pi k upon mu. So the energy change is nothing but energy of radiation that is absorbed by the molecule. So is equal to H nu, which is equal to delta E, and this entire thing is written here as it is. Now, if you will compare this to equation, H and H will get cancelled, and we can substitute nu using this formula. Okay, so what we get is V bar, that is the wave number, 1 upon lambda okay, ये इधर से आया है, this thing is coming from here, so it will be 1 upon 2 pi c multiplied by k mu. So all these are constants, so we can calculate it as wave number is equal to 5.3 into 10 raised to minus 12 multiplied by k divided by mu. Now this k is related to the bond force between two atoms. This is given here for single bond. If there is double and triple bonds are present, okay, if there are double and triple bonds are found by this same means, to have force constant, that is value of k, about 2 to 3 times of the normal value. The values are like this for double bond and triple bond respectively. Now in the equation, V bar is the wave number of an absorption peak in centimeter inverse. K is the force constant for the bond in measured in newtons per meter. C is the velocity of light. The reduced mass mu is measured in kilograms. That small k has been found to lie in the range between 3 multiplied 10 raised to 2 and 8 multiplied by 10 raised to 2 newtons per meter for most single bonds. And if you take the average, the middle point of it, which is 5 to 10 raised to 2, that serves the best, you can say best the purpose. Now next comes selection rules. Now what is being selected here in selection rule? The molecule from one vibrational level to which vibrational level it will jump. Okay, it is determined by selection rule. Selection rule is a statement about which transitions are allowed, which jump, which change is allowed for a molecule. Atomic and molecular species contain very large number of states in which energy can be distributed, although generally only the states lying lowest in the energy will be thermally populated. Simply means in given population of atoms or in given population of molecules, all the molecules, all the atoms will go in least energy state. Okay, so this statement means that if electromagnetic could effectively stimulate transition between any of the states. Atomic and molecular spectra would be complex. It means simply if electromagnetic radiation falling on the population, which is at ground state, and the radiation, if it produces multiple transitions, the resultant spectra is complicated. If the electromagnetic radiation is producing, say, one or two transitions only, the spectra obtained will be simpler to interpret. Selection rules, however, limit the possible transitions and render this amenable to analysis. So, because of selection rule, which is present naturally within the molecules, transitions are, say, discrete and they can be interpreted. Some transitions are allowed by the selection rules, while others are forbidden. This is very similar what we have observed in UV spectroscopy. Quantum theory indicates that only transitions that can take place are those in which vibrational quantum number changes are unity. That is, if the molecule at nu 0, it can change to nu 1 only. If the molecule is at nu 1, it can change to nu 2 only. If molecule is at nu 2, it can change to nu 3 only. The change from nu 0 to nu 2 or change from nu 1 to nu 5 or nu 4 is not allowed. So, that is, the selection rule states that delta nu is equal to plus minus 1 is the rule. Because the vibrational levels are equally spaced for harmonic oscillator, only single absorption peak would be observed for a given vibration. Now, this is the region of the motion where the molecule is behaving as harmonic oscillator. That is, we are talking about this part of the spectra, the lower part of the spectra. In that region only, the rule is applicable. Okay. In addition to the delta nu plus minus 1 rule, there must be a change in the dipole moment during the vibration. So that was the basis of the IR absorption. Okay, there are few concepts. I need to repeat the overtone concept. At higher quantum numbers, okay, that is at in this region, quantum numbers or higher, can say vibrational quantum numbers, where vibration levels are closely arranged to each other, delta E becomes smaller and the selection rule is not followed. The rule that we have seen just now, because the vibration levels are closely arranged, the rule is not followed. As a result, weaker transitions called overtones are sometimes observed. These transitions corresponds to delta nu plus minus 2 or plus minus 3. Okay, but note that because the energies are closely arranged, the energy associated with these transitions is small. That's why these overtones are weak in nature. Okay, the frequencies of such overtone transitions are approximately 2 to 3 times that of the fundamental frequency. The intensities are lower than that of the fundamental frequency. I will show you, I hope you have studied this in your B Pharm, but I will give you one example. Suppose one P is observed for, say, carbon oxygen bond. Okay, suppose this is the peak of, say, because its fundamental peak and it is very strong. It will be around something 1800 or something. Okay, so you will get at 3600. Okay, so the frequency of it is almost double. See, is almost double, but the energy associated is very low. That is also called as something as combination frequencies. See, in a molecule, there are multiple bonds present. For example, in that two of the bonds are vibrating at very close frequency. Combination is related to that, huh? Different frequencies to give absorption peaks with frequency that are approximately sum or the differences of their fundamental frequency. I will give you one example, hypothetical example. Suppose in a molecule there is, say, carbon oxygen bond and say carbon nitrogen bond. If carbon oxygen bond is present as a single bond, is vibrating at say 1800 something, and carbon nitrogen bond where it is present as a single bond, isolated bond, it is vibrating at say 1750. So both of them are very close to each other, and when they are present in a molecule together simultaneously, they are present. So you may observe something like this. So it has both the frequency have got added and you have got combination frequency. I think vibration modes we will take in the next lecture, degrees of freedom, factors influencing